Well, hello everyone. We are ready to begin Unit 3 of this course. Unit 3 is all about MOS electrostatics. This is a really important topic for MOSFETs. This unit is going to be a little bit longer than the other units because there's a lot of material to cover and it's so important to the understanding of transistors. So I hope you'll stick with me and we'll get through this together. Now, just as energy band diagrams are useful for understanding any device, it's a really good place to begin. We're going to begin by understanding MOS electrostatics through the use of energy band diagrams. So we use these energy band diagrams to understand current flow. Current flows when we push energy barriers down. When we write equations for the current flow, we can write current as proportional to charge times velocity. The charge is coming when electrons hop out of the source into the channel. So when we focus on the charge, we're focusing on MOS electrostatics. When we focus on the velocity, we're focusing on carrier transport. Unit 3 is all about electrostatics. Unit 4 will be all about transport. But before developing analytical expressions for the current, doing analytical expressions for the charge density, we should understand things qualitatively with energy band diagrams. So a MOSFET is a two-dimensional device. It's really a three-dimensional device. So the electrostatics can get quite complicated. There's a direction normal to the channel. There's a direction lateral to the channel, along the channel. There's even a direction out of the page and perpendicular to the channel. The energy bands, the conduction and valence bands, move up and down as the electrostatic potential moves up and down. Understanding MOS electrostatics is all about understanding this two-dimensional electrostatic potential in the device. And that's controlled by the voltages that we apply to the device. So solving for that potential really means solving for the Poisson equation. One way to write the Poisson equation is divergence D is equal to rho, where remember D is a displacement field. The displacement field is the dielectric constant times the electric field. So we'll write it as relative dielectric constant of the semiconductor times the permittivity of free space epsilon naught times the electric field. Now you may also remember that the electric field, the definition of electric field is it's minus the gradient of the electrostatic potential. So we could put that together and write the Poisson equation as del squared psi, the electrostatic potential, is minus charge density divided by epsilon, dielectric constant. That would be the two-dimensional Poisson equation. And what we're after is understanding the solutions to that equation in a MOSFET. Now, in general, that's a complicated equation to solve. So we're going to be aiming to try to understand qualitatively the function of that solution. And I'll just point out that the charge density here, there will be charge due to mobile holes and electrons. If we have an N-channel device, it's mostly electrons. If we have a P-channel device, it's mostly holes. But then we'll also have dopants, Nd and Na. And that determines our charge density in the Poisson equation. But it's much easier to draw an energy band diagram and figure out what's going on qualitatively before we attempt to solve this equation. So let's begin by looking normal to the channel. We call this an MOS capacitor. So we'll ignore the potential variation along the channel. We'll assume we have a very long channel device. Things aren't varying rapidly in that direction. And we'll ask what happens when we apply a voltage to the gate. What does the energy band diagram look like in this Y direction? So we'll have something like this. We have a gate electrode out here. We're going to actually have a dielectric insulator in between, and then we have a P-type semiconductor in this example. If we apply a positive voltage to the gate, that'll put positive charge on the gate. That positive charge is going to repel the positively charged mobile holes in the semiconductor and push them away from the surface. When it pushes them away from the surface, it's going to leave the P-type dopants there. Remember, the P-type dopants are negatively charged when they're ionized and doing what they're supposed to be doing and doping the semiconductor P-type. So we're going to have a region that we call a depletion region. It is depleted of mobile carriers, of mobile holes, because our positive voltage on the gate has pushed them away from the surface. It's depleted to some depth, W sub D. If we plot the electrostatic potential versus position, we can qualitatively say it's going to do something like this. If we ground the bottom of the wafer, make that our reference 0 voltage, we know the voltage is positive on the gate. So as we get close to the surface, the voltage in the semiconductor is also going to get more and more positive as it feels the influence of the gate. So it's going to look something like this. Now, there's a very important potential that we're going to talk about frequently in this unit, and that's the surface potential. That's the electrostatic potential at the surface of the semiconductor. It's actually the total voltage drop across the semiconductor because we're assuming that the voltage is 0 deep in the bulk of the semiconductor. That's our arbitrary 0 reference voltage. Well, energy bands go down when the potential goes up. So this varying potential is going to give us some energy bands that bend down near the surface. Fermi level will be constant since I'm in equilibrium in this example. And this is a p-type semiconductor. There's lots of holes. There are a few minority carrier electrons. All right, so what we want to do now is to understand how these energy band diagrams are going to change as we apply different voltages to the gate. Remember, when we do that, as we're reading the energy band diagram, if we want the potential, we flip it upside down, we would see that the potential is increasing as we get closer to the surface, just as we saw on the last slide. The slope of the energy bands give us the electric field, so we're seeing a positive electric field in this region near the surface and a 0 electric field in the bulk. All right, let's begin with the simplest possible conditions. Flat band, nothing is happening. We apply 0 voltage to the gate. Fermi levels all line up. There's no band bending. The potential is 0 everywhere. So actually, this situation, I'm labeling this not the gate voltage, but the gate voltage prime, because this is a special hypothetical situation. We've picked a metal that has its Fermi level that just happens to be in a place where it lines up with the Fermi level in the semiconductor. Now, that's not very likely for that to happen. And we might change the doping in the semiconductor, and then we would have to hunt for another metal that had a Fermi level to line up. So we're going to have to account for that. That's something known as a metal semiconductor work function difference. And we'll have to come back and account for that later. But right now, we're going to assume that we have a hypothetical metal where when we apply 0 volts to the gate, its Fermi level lines up with the Fermi level in the semiconductor, wherever that Fermi level happens to be, which is set by how we doped the semiconductor. So whenever I refer to Vg prime, the prime means it's this idealized metal. It's easier to understand this way, and it's easy to fix up later. All right, when I apply a positive gate voltage to the gate, a positive voltage pulls the Fermi level down. It pulls the electrostatic potential. A positive voltage pulls everything down because all of the energy gets pulled down with a positive electrostatic potential. So when we apply a positive voltage to the gate and pull it down, we also pull down the bands in the semiconductor near the surface. That's what we've seen before. We're going to set our arbitrary reference for potential to be 0 in the bulk of the semiconductor. That's just arbitrary. We can choose our reference anywhere. This is a commonly used one. The energy bands bend down when the potential becomes positive. So as we go towards the surface, we're going to see a larger and larger electrostatic potential. We just measure it by how much the energy bands are pulled down. And there is a critical potential here at the surface potential that is going to play a key role in how we understand MOS electrostatics. Okay, so let's apply a negative voltage to the gate. If we apply a negative voltage to the gate, that raises the Fermi level in the metal. That pulls all of the energies up because a negative potential pulls the energies up. The bands bend up in the semiconductor. We refer to this as accumulation because you can see holes are piling up near the surface. The surface potential now is less than 0. It's negative. That bends the bands up. When the bands bend up, the hole density increases exponentially near the surface because it depends on the separation between the Fermi level and the valence band, which is getting reduced. So we get large numbers of holes that pile up, If we integrate into the depth to find the total number of holes per square centimeter, we can find the total density of holes. If we look at the charge density, we have positive charged holes. We have negatively charged acceptors. We're neutral in the bulk of the semiconductor, where we have an equal number of holes and dopants. But near the surface, we've pushed all of the mobile, or near the surface in accumulation, we've piled up excess holes, so we have more positive charge. When we do this integral, we would find the charge density in coulombs per square centimeter. And that charge density in the semiconductor, Q sub S, will play an important role in our discussions. So, accumulation charge piles up very near the surface and very rapidly as we apply a negative voltage to this P-type semiconductor. Well, what happens if we put a positive voltage on the gate? We pull everything down. When we pull everything down, the surface potential is greater than zero. The bands bend down. There is now a charge density. We've pushed the mobile holes away from the surface. We've left behind the negatively charged acceptors. So in this region WD, in this depletion region, there will be a space charge density. And since we've pushed all of the mobile holes away, and since we don't have many mobile electrons because we haven't pulled the conduction band down close to the Fermi level yet, we only have the charge due to the ionized acceptors. So the charge is very simple. In this depletion region, it's just minus Q times the P-type doping density, the ionized donor density. This we call the depletion charge, due to the dopants that were left behind when their mobile holes were pushed deep into the semiconductor. Deep in the semiconductor, everything balances and the charge is zero. Now, if we continue to apply a positive voltage and we pull the bands down further and further, we'll deplete deeper and deeper and deeper. Eventually, we'll pull the conduction band down close to the Fermi level. Okay. Now we're going to get a significant concentration of electrons. In the bulk, there weren't many electrons at all. They were minority carriers. The number, remember that NP is equal to Ni squared. So the number of holes in the bulk is Ni squared over the doping density in the bulk. That's a very small number. But as the conduction band is pulled down, the electron density is going to increase exponentially. It's going to increase exponentially with band bending. So at the surface, the concentration of electrons will be what it was in the bulk times e to the q surface potential over kT, which can be a very large number. So we can end up with a large number of electrons in this p-type semiconductor. So that large number of electrons makes this p-type semiconductor n-type at the surface. We say that we have inverted the semiconductor. We've inverted it when the concentration of electrons at the surface is equal to the concentration of holes in the bulk. The surface is now as n-type as the bulk was p-type. So this we call the onset of inversion. We can simply solve this equation and determine what surface potential it takes to achieve this condition. And the condition it takes, we'll find out, is very simple and easy to understand. So basically, in the bulk, the hole concentration is related to how far below the intrinsic level the Fermi level is in the bulk. All right. That's a quantity that we call psi sub b. When we express that energy difference, EI minus EF, in units of potential, we call that psi b. And it's easy to solve these equations and find that psi b is kT over q log Na over Ni. Now, at the surface, the number of electrons at the surface, when the number of electrons at the surface is equal to the number of holes in the bulk, we say the surface has been inverted. And you can see that in order to do that, we have to pull the Fermi level as far below the Fermi level at the surface as it was above the Fermi level in the bulk. That requires a band bending of 2 times psi b. That's the criterion for inversion. That's going to be a very important criterion for us. Once we have achieved a surface potential that bends the bands by 2 psi b, we have inverted the surface, and it now becomes the opposite type that the bulk is. So we can easily, knowing the doping density of the semiconductor, we can easily compute what surface potential will invert it. Okay. Now, as we keep inverting the semiconductor and depleting it, we will find that it is very hard to bend the bands even further as we apply more and more gate voltage and try to push the depletion region deeper and deeper. The number of electrons at the surface will pile up exponentially, and they will screen the charge on the gate, so that basically everything happens at the surface. There'll be a very strong electric field in the oxide, but the depletion region will be pushed to some maximum value. And it is very hard to bend the bands more than 2 psi b, because now the electron density is increasing exponentially. Just a little bit of additional increase in surface potential exponentially increases the number of electrons. Okay, so we are able now to qualitatively understand how the charge in the semiconductor in coulombs per square centimeter. So this is the total charge when we integrate into the depth of the semiconductor. It's not the charge density per unit volume. It's the charge density per unit area when we integrate in the depth and total up all of the charge. When we apply a negative surface potential, we bend the bands up. Holes accumulate rapidly very near the surface. We have a very large positive charge. In fact, we will see that it increases exponentially with surface potential. When we apply a positive voltage to the gate, we push the holes away, we deplete the semiconductor, and we start to get charge. It'll be a negative depletion charge. We're plotting the magnitude of the charge here. And we will see in the next lecture that it increases as relatively slowly as the square root of the surface potential. But once we hit this critical potential, 2 psi b, the inversion layer charge will now begin to increase exponentially, and the charge will very rapidly increase. So that qualitative understanding of charge versus surface potential is very important for understanding MOS electrostatics. As a test for how well you understand those concepts, redo all of those diagrams assuming an N-type substrate, and redo the charge versus surface potential plot. All right, so just to summarize, our look at MOS electrostatics through energy band diagrams has given us a very simple understanding of how the charge in the semiconductor is going to vary with the band bending in the semiconductor as measured by the surface potential. We have this flat band condition that's our reference point where there is no band bending. It occurs at 0 gate voltage for this ideal hypothetical metal. We'll fix that up later. If we apply a negative gate voltage, we bend the bands up, holes pile up near the surface. We call that accumulation. We're accumulating majority carriers near the surface. If we bend the bands down, we first deplete the semiconductor, we push the mobile holes away. If we continue to apply a bigger voltage, pull the bands down even more, we eventually invert the surface and it becomes N-type. So that's depletion and inversion. So energy band diagrams help us understand charge versus surface potential. We're going to try to write some equations later and see if we can describe those, but the energy band diagrams help us understand it. So our next topic in the next lecture will be to solve this Poisson equation. In general, that's very difficult. In general, we'll need a numerical solution on a computer. But in depletion, we can actually solve the problem analytically. And we can make a widely used approximation in this region called the depletion approximation, and we can solve the MOS electrostatics problem. This is a widely used approximation that often gets us the answer that we were looking for, and we'll see how that works in the next lecture.